Hello, everybody. Thank you for joining. My name is Mike Huff. I'm with GROB Systems. Today, we're going to talk to you about a mold and die workshop that we did at the EMUGE-FRANKEN Technology Center in Massachusetts. We did this in partnership with EMUGE and Open Mind Technologies. So the layout of this webinar, we're going to take roughly 45 minutes to 1 hour's time. We'll do a quick intro of the companies, and then we'll move into a demo portion and get a little more technical. After the presentation, we'll have a video that will show the overview the process that we used to create the part. And once that's done, we'll have a quick Q&A session. So if you have any questions along the way, feel free to enter them into the chat box and we will get to as many as we can at the end of the presentation. So with that, I will hand it over to Kevin Gaddy.
Thank you, Mike. My name is Kevin Gaddy, GROB Systems. Give you a little overview of GROB. GROB is a German machine tool company headquartered in Mindelheim, Germany. There's 5 plants throughout the world. Each plant builds the same type of product. And so in the United States, we're supported by GROB in Bluffton, Ohio. The Bluffton, Ohio facility is approximately 400,000 square feet. There's approximately 800 people there at this time. You get a little bit overview of the size of the company, 400,000 square feet, with the engineering, administrative, sales, and service. Everything comes out of Bluffton, Ohio, to support the North American market, along with Mexico and part of Central America. In Bluffton, we have systems machining centers, which is high production, 24/7 machining lines that usually you'll find in automotive. We also have assembly technology, which designs and builds machines that assemble components related to the automotive industry. We also have e-mobility battery technology, which is one of our fastest growing areas, and that's supporting the building of batteries, obviously, and e-vehicles. And what I'm part of is the horizontal 5-axis universal machines. These are standalone or multiple 5-axis machining centers used for high production facilities or job shops. A quick overview of our line of machines. You can see that they're all similarly the same because our kinematics stay the same across this whole product line. So the G150 up to the G750 in the top row, what differentiates those machines is just the size capacity of the component and the pallet system. And you can see in the middle, we have our lower price line. And of that, the G550A is the machine that we used here at the EMUGE Technology Center. On the lower line, you can see that we also offer turning capabilities with that 5-axis platform. Some of the advantages of our design, the GROB system. We have quite a bit of, A-axis stroke. It's the largest that you'll find in the industry. It enables us to do overhead machining. One of the benefits of having that swing is that it's easy to clean off our pallets, wash them down, get chips out, so it's easy for automation. You can see that the swivel range is going to be larger than standard vertical machines are on the market. We don't have any interference in our work envelope. And that enables us to have maximum tool lengths across our product line. Our spindle sits on a carriage that's in a tunnel, so we don't take up any room in the work area with the spindle itself. And it enables us to be able to have longer tools that we can project past center. And then the horizontal spindle concept, like I said earlier, cleans out the work area so you're able to flip the part upside down. And that gives you, as I said earlier, a good way to clean it, but also access components, part of the component that, is a unique tangent point. In the US, we're set up to support, like I said, North America, Mexico, Central, and we do have application engineers stationed there. We have service coming out of there. We do have a crew of mechanics that we call them that build the machine, that are able to go out and support the machine. We have our sales based out of Bluffton, and we're also a hybrid, is that we do have somewhat of a dealer network in different parts of the country.
Hi, everyone. My name is Ernie Dickinson, and I'm representing Open Mind Technologies. We developed a product called Hypermill. Hypermill has been around for roughly 25 years. We are a global company with 17 subsidiaries and over 50 resellers. You can see we have many licenses out in the field, many customers covering many different industries. Our global headquarters is in Munich, Germany, where we develop the software. Locally here, we are decentralized and based throughout the United States and Canada, as well as Mexico and South America. Primarily, we sell direct. We do have some dealers in some small locations, but for the most part, we are selling direct to our customers. If there's a problem, you come to us. We can go directly to the developers. There's really no middleman for us. We have staff located in 9 states through the more industrial part of the country. Here you can see our entire staff. Everybody in this picture has at least some 5-axis experience, a lot of number of years in the industry doing many different types of parts. We do our own local post-processor development, as well as develop directly in Germany, especially for the more international machine tools like the GROBs. We offer hotline support. So you call us, we have an 800 number. We'll get on with you and do a webinar and make sure you're squared away. Also, we offer training as well, either direct or online, part consultation, and also partner collaborations as well. So in this slide, we want to sort of showcase that with CAM, it's more than just creating toolpaths. CAM has become more of a nebulous thing where it's controlling the whole process digitally. That would be virtual machines, post-processors. We offer automation. We offer additive manufacturing. So a bunch of stuff on top of just the standard 5-axis programming is offered inside Hypermill.
All right. Hello, everybody. My name is Evan Duncanson. I am a milling support specialist here at EMUGE-FRANKEN, and we're just going to go over a company overview of EMUGE-FRANKEN as a worldwide company. So EMUGE was established in 1920. There is over 1,900 employees worldwide, 9 production facilities worldwide. We have over 110,000 stocked items, different part numbers, global support, obviously, and we are also privately owned. The current owner of the company is the son of the founder, and his 2 son-in-laws help him run the company day to day. So for manufacturing in Germany, EMUGE is based in Lauf, Germany, about an hour or 2 away from Munich. And EMUGE makes everything, from taps, thread mills, drills, holders, work holding, kind of the whole gamut, other than our milling products. And our milling products are made by Franken. So we are the same company, but we still have the 2 different names. So Franken is based in Ruckersdorf, Germany, about 15 minutes away from Lauf and EMUGE. They're right down the road from each other. And they make, like I said, everything milling and also some tool holding, specifically for milling. And they were just established in 1916, so Franken is actually older than EMUGE. EMUGE purchased them about 60 years ago, so now we're one company. Franken is comprised of over 400 employees, and like I said, they're in Ruckersdorf, Germany. Here you can see the state of state-of-the-art equipment and processes we have at EMUGE and Franken. Everything is very clean, up to date, very well organized, and the flow of the tools is very well managed throughout the production facility. So they go from stage to stage and kind of go from back to front of the factory. And then here in West Boylston, Massachusetts, that's where we're located. So we're the EMUGE-FRANKEN location for the US and Canada. We have over 26,000 square feet of manufacturing space in our new building. We doubled the size of our building a few years ago, and 26,000 square feet of that was for manufacturing. So those are full of Anka machines for special and standard end mill production. And then we do also have a PVD coating vessel, so we can do coatings of end mills and drills and all sorts of other stuff in-house as well. Along with actual manufacturing, we have our technology and training center. So our technology center has the GROB 550A machine, and then we have several training rooms, of various sizes that we can hold trainings or events or anything like that. And we like to use the training or the technology center as much as we can for test cuts and events and all sorts of stuff that we can actually, use the tools and cut material. And then EMUGE and Franken are always, continuously improving and doing a lot of R&D with different, revolutionary ideas or tools. So these are just a couple. The punch tap and the tap tour are currently the fastest way to make a thread in cast material for like the automotive industry. The self-lock thread is a self-locking thread, as the name suggests, that locks the bolts in the thread and does not let excessive vibration pull the bolt out of the threaded hole. Our circle segment tools, that's for faster finishing with 3D 5-axis toolpaths. Our Pagodi cutter is a new version of our of like a Christmas tree cutter or a fir tree cutter that helps stabilize the process so much that we can go up to 10 times faster feed rate and have 10 times longer tool life as a regular fir tree cutter.
So here today, the die mold workshop, this is the component that we're going to cut. The component is just a generalized component that has certain features on it. And looking at the G550 Access series, which is the 550A, you can see that we're outfitted with an HSK 63 16K spindle that can generate 42 horsepower. The tooling capacity of this piece of equipment is 50 tools. You can see that the axis travels over there on the right. It does come with a high pressure coolant system, and we do have a Siemens control with our GROB interface. And our work area is capable of handling a 630 millimeter pallet. And on a diametrical, it can handle up to 35.4 inch diameter, max weight of 1,300. Here's some more information about the component. It's a 4140 steel component. It's relatively small compared to the size of the machine, 8x4x2. And yes, you'll find this in die mold, automotive, and other industries.
Yeah, so we're going to talk about the roughing tool that we're going to use to rough out the part here. It's a multi-cut duplex, and there's several key features that I want to go over it that kind of make this tool an all-around just very, very good tool for roughing out, die and mold parts. So the first feature on this tool is the duplex geometry. So the duplex geometry actually is the high feed end on the end of the tool. It has a negative rake angle, so it actually pushes the material instead of cut it. And because of that, you can actually increase your chip per tooth significantly. You can go up to 40 thou chip load with a very shallow depth of cut, but a very large step over and a very large chip per tooth to just kind of blast through that material and cut out a lot of material, with this high feed strategy. One more feature of this tool is the variable flute spacing and the variable core diameter. So the first, 1/2 of the flute there from the end of the tool, it actually has a much smaller core diameter than the second half. And that's because, if you want to slot very aggressively with this tool, having a smaller core diameter with bigger flute channels and more chip space just allows you to get the chips out of there and really, blast that material. But then the second half has a much larger core, so if you want to use it in a more long length of engagement using the whole flute length, it's a much more rigid tool than having that small core all the way up. Also, the multi-cut feature of this tool, that refers to the roughing profile. So it's essentially a high performance new version of like a corncob rougher. And this roughing profile reduces the cutting forces by about 40% on the spindle, just because you don't have that one smooth edge in contact with the material at all times. You have a lot of these tiny little teeth, and it reduces the amount of forces. And then you can see in the picture there, that's actually the chip formation on each one of those little teeth. So it produces very, very small chips that are very easy to evacuate and get out of the way. One more feature of the Duplex series is it comes with coolant through. So some of the Duplex tools are solid, and some of them have an axial coolant hole. So normally with cutting steel, we would suggest using just air, just an air blast. But if you have, a part that has a small pocket or something like that, and you're having a hard time getting the air down in there and clearing the chips out of the way, and you're kind of packing chips and double cutting chips, the coolant through can be utilized to, blast those chips out of there and get them out of the way. And, then you can actually increase your metal removal rate because of that. One more feature of the Duplex series here is the coating. So the coating on this tool is a TiALN multi-layer. It's actually a really interesting coating. So it's not just one layer of TiALN, it's several layers. And what's interesting about this coating is when you put some heat into it and you get it to a certain temperature, it actually creates an oxide layer on the outside of the coating and kind of changes its structure and its characteristics, and actually becomes harder and lengthens the tool life significantly. If you weren't putting as much heat into it, it's not going to hurt the tool at all, but actually, getting some heat into there and everything will actually prolong the life of the tool, surprisingly. And then one last feature of the Duplex series is the carbide. So it's a very high grade sub-micro grade of carbide, very high hardness, but it also has some flexibility in there. So because, you're going to be using this in very high feed rates and very high, force applications, maybe, doing very heavy slotting, a higher hardness, more brittle carbide is just going to break down a lot faster because it's not going to allow the tool to kind of move around just a little bit that it needs to be able to slot aggressively. And this carbide can do that.
On the GROB, as I mentioned briefly earlier about the horizontal spindle, you can see here in this animation is that on the left side, the horizontal spindle, we're sitting on a carriage that has linear guideways. And there's 3 trucks on each side of the spindle for a total of 6 trucks. So as the spindle moves out into the work area and engages the component, we have the ultimate rigidity. We're not extending beyond the linear rails or the carriage. And as you can see that we can approach and pass the center of that table. On the right side, you see the animation of a vertical 5-axis as a trunnion table underneath. And as that spindle comes down, it projects outside of the trucks. So you have a large unsupported area the closer you get to the table. GROB firmly believes that the horizontal approach is the most rigid, most flexible, and the easiest to use. Another thing about, the application is we're really concerned about, having short tool length. And doing that in a horizontal plane is a lot easier than doing it on the vertical plane, as we just saw in the last slide. So we have a really short area between the tip of the tool and the face of the spindle, and we're able to maneuver that component in front of the tool to get the tightest type of arrangement for the most rigidity. And this also shows you the 3 different tools that we used in this demo to maximize, the rigidity.
Awesome. So I just want to talk about the tool holders we used on this part. So we used our FPC milling holders. They're actually made by Albrecht over in Germany. And if you're not familiar with Albrecht, they actually created the keyless drill truck many, many years ago. So they are they've been around for a long time, and they are always kind of on the cusp of what's possible, and always coming out with cool, interesting things. So this holder, it's a collet system, and it uses a worm gear. So you turn the set screw on the side there, it turns the worm gear, tightens down on the thread on the collet, and pulls the tool in with over 3 tons of gripping force. And what this tool holder is capable of is, it has the high rigidity of like a shrink fit holder, but also has a lot of dampening involved because of the construction of it that kind of emulates a hydraulic holder. And then, even more so, we have a pull-out protection option that we call our pin lock system. So it's a special collet, not a special collet, but it's just a different version of the collet that has a hole drilled through the side of it. So you put a pin through the hole across the welded flat of a normal tool, and it, produces a positive locking system there. So there's no way of that tool pulling out. So now you have the rigidity of shrink fit, the dampening of hydraulic, and the positive pull-out protection of a weld and holder, while still holding 3 microns of concentricity on the run out of the tool. And then you can see on the right, there's different gauge lengths and different designs of this holder. So all the way on the right, we have our slimline design, kind of emulates the nose of a shrink fit holder, getting down to a much smaller diameter. And at the bottom there, we have our micro. So it's a much smaller tool holder, to get the maximum amount of maneuverability in, 5-axis tool paths. And this is a test one of our customers did on one of their FPC holders. So they have this force measuring tool here that it actually is specifically made to measure the force that a holder grips a tool. So on the left, they have a hydraulic holder. That's a 3/8 diameter hydraulic holder. In the middle, they have a hydraulic holder with a sleeve. So it's a 3/4 holder with a 3/8 sleeve. And then on the right, they have an FPC 14, which is the smaller version of the holder. We also have the FPC 20 that's mostly used for, your heavy roughing, with a 3/8 collet. And you can see the top number on this gauge here. There's no units on the number. It's just kind of clamping units. So we have 49 units of clamping on the hydraulic holder, 124 on the hydraulic holder with the sleeve, and then 854 with the FPC. So you can see just how much more rigid and how much more clamping force there is on the FPC than that hydraulic holder. And then we're not using circle segment tools on this part, but I always like to talk about them just real quick. So if you're not familiar with the circle segment technology, it essentially takes a ball mill, you zoom in on it, and then you take a small segment of that ball and you put it on a tool. So for instance, a taper form end mill, one of the shapes that we offer, say you have a 16 millimeter shank, and that might have a 1,000 millimeter cutting radius on it. So it's like using a 2 meter diameter ball end mill, but on a 16 millimeter shank tool. So because of that, you can then increase your step down or step over, many, many times, from say maybe 5 thou to 80 thou or something like that. And that just decreases your cycle time to finish a part. There's 4 different types or shapes that we offer. So the taper form up at the top is like the one I was just talking about. That offers the largest radius option of all the tools. And then the oval form is kind of the next option that I like to go with if I can't fit a taper form in there. The oval form has a smaller ratio from the shank to the cutting radius, but because of that, it can fit into other areas that the taper form might not be able to. Then the lens form, that's mostly for shallow floor finishing, say a tire mold or something like that. And then the barrel cutter, kind of a standard barrel shape, that's mostly only used for undercuts.
On the GROB, tool length and diameter, we use a DigiLogic from Bloom. The DigiLogic is capable of handling a lot of different geometries that are on tools, just like Evan mentioned. So it can handle the barrel shaped tools, the oval forms, taper forms, and lens shapes tools. This is just showing you a little bit of a graph and simulation of measuring a barrel shape or style tool and the typical readouts that you're going to get from it. This is going to be a little bit of a video showing you of that operation inside the GROB. A couple of things to pay attention to. You see that the spindle is working out of its tunnel. It's not really inside the work area. And once we flip the table over to get to the bloom, most of the chips and the splash go away. And so we have a nice access, to the bloom laser. One of the other options with the GROB, and part of the design and build of it, is that we can use longer tools right out of the tool changer without making any alterations to the tool changer. You can see on the left side there, the machines, 150, 350, up to the 750. It gives you the idea, gives you the numbers of the longest tool that you can put in the tool changer, and that'll swap out in the operation. So on the 550, you can see that standard, we can put an 18.3 inch long tool in there. So the flexibility of that machine is pretty immense when you look at the length of tools that you can accommodate in regular operations.
Thanks, Kevin. At this point, I want to talk about some of the programming techniques and tools inside the CAM software we used for this part. The first one I want to speak about is our automatic extension of milling surfaces. This is done based on whatever boundaries we're picking. And essentially what it is an automatic way of extending those surfaces. So there's a nice runoff with the tool path. So you're not starting and stopping on actual material. This is all done automatically inside the software. In the old days, it was very common for people to construct these surfaces using the CAD system. But now we've integrated some of that CAD power inside the actual tool path itself with some knowledge of where they actually be and how far they have to go for it to work. So this is implemented in a few of our cycles, the 3D profile finishing, the 3D Z-level shape finishing, 3D corner rest machining, 3D equidistant machining, and also our 5-axis tangent machining. And this list is ever increasing, so we're adding it in places where we feel it's needed moving forward. So, a second tool we use to sort of go along with the automatic surface extension is our smooth overlap function. So the smooth overlap can work in conjunction with the surface extension, or it could be on its own. And essentially what this does is it adds some extra tool path to the intersection between other tool paths, and it starts off the part a little bit. So it's no longer, you're not coming down, starting on a previously machined area and then working into the area you want to machine. It actually builds in a smooth transition from one area to another. So we feel this is a game changer when it comes to mold and die applications. Anytime when there's transitioning between surfaces, this is a very powerful tool to make sure that transition is as smooth as possible and you don't see any start and stopping or any difference between the tool path. This is supported, once again, a list of what this is supported in for us. And for sure, this is a ever-growing list, but right now it's 3D profile finishing, 3D Z-level shape finishing, 3D Z-level shape finishing, and our rest material cycles. In this picture, you can kind of see with and without. This is just like a simple 3D ISO on a fillet. You can see without the smooth overlap, it starts on the surface, on the tangency point of the surface, and it ends at the tangency point of the surface. Automatically, the system will put in a couple extra passes that sort of curl into the tool path. It's not just a simple extension. There is some lift to that as well. That way, as you're transitioning from the horizontal to the vertical, more vertical surfaces, once again, you don't see any overlap. Anytime maybe there's spindle growth or tool wear, this smooths that transition between those two areas. And one last picture, just showing you that little lift. Once again, so we're not starting in the material and sort of moving into it. We're actually off it a little bit, and we slowly move down into the material and then slowly move off on the other end, guaranteeing that smooth transition. And inside the software, and this is something that Hypermill is very good at, is taking something that's actually kind of complex internally and making it really simple for the user. So for the automatic surface extension, it's just a matter of turning it on and off, and then you can control the length. You can either have an automatic control or you can do it manually. And then the smooth overlap is essentially a click box. It's a simple click box. You turn it on, and it's there, and it'll automatically do the distance you need and the transition, and you don't have to worry about how far and how much you need. It's all automatic with just a simple click box.
In this slide here, going to show you a few things that, or one thing that we did for this application. On the left side, you can see how we have this mounted on a pallet on our rotary table, but we have it kicked up at 30 degree. The reason we did that is that you look at the right side of the screen and you can see the top animation. That's showing you that if we put this right on the table itself without kicking it up at a 30 degree, you'd actually see more rotation in that in 5 axes. And to do that, or to control that, that's why we kicked it up off at 30 degrees to minimize the rotation. This machine, 550A, does have a worm-driven rotary, so it's not a torque motor. So you don't want to introduce any more inaccuracies or heat than you have to. So you want to be nice to it so it actually can perform for you. And so you can see something as simple as that, of kicking it up 30 degrees is going to minimize all your rotation when you're doing true 5 axis. Another feature that we can use, we didn't use it on this one, is that we have a calibration system that calibrates the kinematics of the machine. We refer to that as GSC, light, and here it says advanced, but it's a light version of it, is where we can probe the ball on the pallet itself. And so when you pallet change, we can actually do a kinematic check And the other method that we have is that you have to have the table empty, put on 2 tooling balls, and go through a routine that it's going to adjust and calibrate the kinematics of the machine. Another feature that we offer, and we don't have it on the machine we used here, is the load-sensitive tuning. So everybody has different weights depending on the component you're doing, and if you leave the axes just as as is, then you might not be getting the ultimate performance if the component is heavier or even lighter than expected. And so the load-sensitive tuning is ability to tune the rotary to the weight of the component. And that helps in maintaining accuracy and performance.
Another tool we use to achieve a really good surface finish on this part is what we're calling our high precision milling. High precision milling is a tool that, to best understand, we have to sort of think of the history of how CAM systems work. When CAM systems first came on the market, essentially what they were doing was applying toolpath to specific mathematical surfaces. If you had multiple surfaces, you ran a situation where there could possibly be a gap between these surfaces. This gap would cause the tool to drop into those surfaces, giving you a gouging situation, which obviously is not what you want when you're trying to get a good surface finish or even trying to make anything. At some point, the industry decided to switch technologies and use a mesh model to check against, essentially taking the groups of surfaces that we had before and turning those into a watertight mesh model that the toolpath couldn't penetrate. So there were no gaps between this. This was much better, and we could avoid the gouging situations, and it was much safer. Of course, the problem with that is any sort of mesh, because it's based on triangles or polygons, would give you a faceted looking surface finish, which you could minimize with machining tolerance and having better machines and higher quality tooling and whatnot. But you would certainly see that in a situation where you had to polish, or maybe like an optical type situation where surface finish was incredibly important. So fast forward to the recent past here, Hypermill was able to come up with technology where we check against the mesh because that's the safest mode of checking. But then we project the toolpath to the mathematical surface, therefore giving us that high surface quality that we remember from the past, where you're actually machining on the actual surface itself and not the mesh. So you can see here in this picture, there's a little bit of inconsistency in the toolpath. Essentially, it's picking up the facets of the mesh. If we click it one more time here, you can see that with our high precision milling mode on, with the extra step of actually moving the toolpath points to the surface, it smooths out the toolpath and therefore increasing surface quality, decreasing polishing time, and giving you a much better looking toolpath in part at the end. Another example, you can see on the right, you can actually see the faceting. It's still a great surface finish. If you ran your finger along this, you'd say, wow, that looks great. But if you went to polish this, or like I said, if this was like an optical type part, you could actually see that faceting, and you would have to work to get that faceting out of there. Where the part on the left-hand side is much better, much cleaner, much more consistent, and all you're really seeing is the toolpath lines. Moving on to the last thing I'd like to talk about with this part is probing. Probing for us is sort of a multi-prong approach. It's not just to check a part at the end. It's not just to set up a part at the beginning. It's something to use throughout the entire process. So in regards to the setup in the beginning of the process, we can use the probe to check the stock. The stock is just a rough cut piece of material. Maybe it's a forging or a casting. Some inconsistent piece of material that we're machining out of, we can check against that. We can align it, we can do a best fit. There's a bunch of things we can do with that. We can also origin the machine with the probe. Maybe you just throw a vise on there and you just take 2 probe hits. There's a probing cycle that will automatically align the rotary axis to match wherever the way the vise is lined up. So you don't have to sit there and tap it in place and put an indicator on it. We can also use it during the process. So perhaps you pre-machine a couple pockets or even finish machine a couple pockets. Since this is fully embedded in the CAM system, right after the pocketing routine, you can grab the probe, come over here, probe a pocket or probe a slot, like it's showing on the left there, and then check that data, and you can either stop the process completely. You could actually use the data you're getting from probing to adjust the cutter comp, and then go back to the original pocketing routine and finish it, fixing the cutter comp to what you need. So a lot of things you can do in process as well with the touch probe. Then lastly, do it at the end. You cut your part. It looks good. Let's check it. Let's make sure it's okay. We can check specific features like holes and pockets. We can check 3D surfaces. Maybe you pick a couple of arbitrary points on the surface, bring the probe in, check it, see how far you're off. Once again, maybe it's perfect and you pull the part off and put on the second part, or maybe you have to change something and then you can always go back and rerun the program, maybe change tools or whatever the case may be. So once again, we look at probing as a something not just at the beginning, not just at the end, something you do throughout the entire process. And having it in the CAM system makes that possible. And then finally, what kind of data did you get back out of this? I spoke about, returning the data back to the CAM system where you change a cutter comp or change a tool, or you could just have hard data. You could just have numbers to look at, and you could see the actual deviation based on what tolerances you're giving it, where you're triggering the probe and everything. So all that can be either read back through the control or through the CAM system.
Another thing to talk about on the GROB is that its efficiency in getting rid of chips and being able to wash out the work area. This is really important if you're doing automation. It's always have a clean environment when you're swapping out pallets. So we have the coolant that comes through the spindle, we have the coolant that comes out of the tunnel, and we have the overhead shower along with the lower washdown areas. Here we see the camera that's in the work area. So we're seeing the component, being roughed out. We're actually looking at the first roughing tool. You can see that we have it pitched up at an angle that gives us the tightest geometry between the cutting tool and the fixture. And you can see that the smooth motion that's going on within that envelope.
Yeah, like Kevin just said, we're using the 12 millimeter multi-cut duplex here. So we're doing a high feed application on the outside, and then on the inside, we helixed in, and now we are, doing a very heavy step over at full depth, and you can see just how small those chips are, getting out of the way because of that roughing profile. Very efficient way to clear the chips and cut that pocket very nicely.
From a CAM perspective, we used a combination of our 3D optimized roughing for the high feed and our max roughing for the more high performance roughing, getting deeper in the pocket. Also using something called plane level detection to pick up any flat areas and automatically put a tool path on those flat areas, ensuring that we leave the right amount of stock everywhere.
And now we're using the 5/16 4-flute ball mill to semi-finish the part. You can see, it's just whipping around the part, finishing all areas of it. And then you can see we're using the coolant through feature on the FPC tool holders. So it's pushing coolant through the collet. So it's emulating a coolant through tool while using a solid tool. So, it's a very efficient way, very high pressure coolant, instead of, just blasting the low pressure external coolant on it.
Using a combination of Z-level shape finishing for the vertical walls and profile finishing for the floors, we were able to cover all the surfaces. Also using our smooth overlap technology and automatic surface extension, making sure the transitions are good. Here we're using our 5-axis rest machine, which will use a combination of fixed 3+2 for certain areas, and also, as you see here, simultaneous 5-axis to get a more consistent tool path for all the remaining areas that have to be machined.
So we're seeing it here, in a finished mode going around. We can just actually see right here that there's not an accumulation of chips on the table or even on the component. That goes back to some of the previous slides that showed talking about the evacuation of chips, in our work area. That helps keep it a lot cleaner, under control, and it makes it pretty easy for automation.
Okay, so we have had a couple of questions come in throughout the event, or throughout the presentation. The first one is for EMUGE. Evan, why did we use a 2-flute ball mill instead of a 4-flute ball mill for finishing?
Yeah, that's a great question. Normally, you want to use more flutes when you're finishing. You get a better finish. You can go a little bit faster with the same chip load, right? But with this part, the geometry with fillets and some corners and stuff like that, a 4-flute was just going to chatter or chirp a little bit, just because it has a lot less flute space and chip space than a 2-flute. So the 2-flute was actually more efficient and was going to give us a much better surface finish than the 4-flute on this specific part.
Okay, thanks, Evan. We have another one that came in. We'll direct this one to Ernie from Hypermill. What types of probes or brands of probes do you guys support with your probing cycles?
Currently, we support the sort of baked-in probing cycles for both Siemens and Heidenhain controls. Those machines and those controls have their own cycles, so it doesn't really matter which probe they have. Also, above and beyond that, for machines that don't have those controls, we support the Renishaw cycles and the Bloom cycles as well.
Thanks, Ernie. So we have time for one more question. I'll direct this to Kevin from GROB. The GSC advanced cycle, is that only able to be ran in between part changes, or also, say, tool changes as well?
So on the GSC, there's 2 different styles. One of them is the main GSC, which means that it's only done, on the table itself. A couple of tooling balls and probing, and it takes about 20 minutes. And that's the GSC that you can't have anything on the table, and it's in between jobs. The GSC Lite, or advanced as we call it, that's the same kinematic check, but it's a lot shorter, and it can be done in between cutting tools. Can do rough semi-finish and do it before you do finish, and you actually can do it between pallet changes. So if you swap out a pallet, bring another one in, you can do the GSC Lite then also.
Okay, thank you, Kevin. Thank you, everybody, for joining us today. That's going to conclude our presentation and our webinar. So if you have any questions afterwards, feel free to contact those people that you see on the screen. There's their contact information listed there as well. Thank you for joining, and we will talk to you soon. Thank you. Bye.